ever just stop and stare at a massive skyscraper? Or a bridge that seems to stretch on forever? These incredible structures, they really are monuments to what we can build. They literally shape our world.
But here's the thing. Every single one of them, every bridge, building, and tunnel, is connected to the Earth. They have to be. They rely completely on the ground underneath them for support. So what happens when that ground just can't hold it? What if it's unstable or too soft? Well, that's the multi-billion-dollar question, isn't it? And there's a whole field of engineering dedicated to answering it.
And that field is geotechnical engineering. It's the science of understanding the ground, literally right beneath our feet, so we can build safely. These are the experts who figure out how soil, rock, and water will behave when you put a giant skyscraper on top of them. So today, let's pull back the curtain and see what a day in the life of one of these engineers is really like.
All right, so for a lot of geotechnical engineers, the day doesn't kick off at a comfy desk with a warm coffee. Nope. It starts out on a construction site. Sun, rain, mud, it doesn't matter. You can't really understand the ground by looking at a computer screen. You've got to get out there and get your hands dirty.
So, before anyone even thinks about pouring concrete, the first job is to investigate what's hiding underground. It's like being a detective. What are we actually dealing with here? Is it soft clay? Is it loose sand? Or are we lucky enough to hit solid bedrock? And the only way to find out for sure is to go down there and grab some samples.
So how do they do that? Well, one of the most common ways is something called the Standard Penetration Test, or SPT. It sounds complicated, but it's actually pretty straightforward. You've got this hollow tube, right? And you drive it into the ground with a 140-pound hammer. The key is counting how many hammer blows it takes to go down 18 inches. That number, the blow count, is pure gold. It tells you how dense and strong the soil is, and you get a nice soil sample packed right inside the tube.
But, and this is important, not all samples are the same. A sample from that SPT test is what we call disturbed. It's great for looking at the basic stuff like what size the soil grains are, but the soil's natural structure is all jumbled up. To test for things like its actual strength or how water flows through it, you need an undisturbed sample. You have to capture it just as it was, deep in the ground. And to get these different kinds of samples, engineers have a whole toolkit. I mean, it can be as simple as digging a pit with a shovel or using specialized gear like a Shelby tube or a piston sampler to carefully slice out one of those pristine, undisturbed cores. It all depends on the ground conditions and exactly what you need to find out.
Okay, so after a morning out in the elements, it's time to head back to the office. This is where the real transformation happens, where all that mud-caked dirt and those scribbled field notes get turned into hard data that will make or break the entire project.
But hold on, before we get into the office work, check out this quote from an engineer on Reddit. It really hits the nail on the head. That time in the field, it isn't just about collecting data. It's about building an intuition, a feel for the earth that you just can't get from a book. And that experience is what makes all the difference when you're back at the desk.
So, with that hands-on experience in their back pocket, the engineer gets down to business. The physical samples become digital models, those SPT blow counts, the notes from the logs, all the lab test results, everything gets plugged into some seriously powerful software. And this digital toolkit is pretty impressive. You've got software like Aldoa, which helps manage all that data coming in from the field, and then you have the heavy hitters, like Plaxis or GeoStudio. These programs run incredibly complex simulations to predict exactly how the ground is going to behave under the massive weight of a new building. Now, all of this work, all the drilling, testing, and modeling, it all boils down to one incredibly important document, the Geotechnical Report. And this isn't just a summary of findings. Think of it as the official instruction manual for the project's foundation. It tells everyone else, the architects, the structural engineers, what they can build on that specific piece of land and how they have to do it.
So, in a perfect world, that's that. A nice, clean process from the field to the final report. But let's be honest, engineering is almost never that clean. Because there's always one variable you just can't control, and that's reality.
And this quote from another engineer on Reddit is the perfect example. Your whole day is planned, the deadline is looming, and then boom, a phone call. A totally physical problem. The drill rig can't even get to the spot where you need to drill because the hill is too steep. Just like that, the entire schedule is up in the air.
And as if that's not enough, your phone rings again. It's the client. Oh, and by the way, they're changing the entire project. They're doubling the weight of the building, and they need that final report tomorrow, not in 2 days. So now, everything you've done has to be reanalyzed, and you have less time to do it.
This, right here, is the real job.
This is what separates a good engineer from a great one. It's not just about crunching the numbers. It's about thinking on your feet, adapting to chaos, and using all that hard-earned experience to solve impossible problems under crushing pressure.
So let's just zoom out for a second. We've seen the mud, the math, the curveballs. But what does it all really mean? Well, it means there's a direct line connecting a single handful of dirt to the entire skyline of a city.
And that's why this matters so much. Geotechnical engineers make our modern world possible. They're the ones who manage the risk of building on this constantly changing planet of ours. They make sure our homes, our bridges, our entire infrastructure are built on solid ground. They keep us safe.
I think this mission statement from a real engineering firm says it all. It's about more than just a project. It's about finding solutions that benefit the client, sure, but also the community and the environment as a whole.
And you know what? This work is never going to be finished. The ground beneath our feet is the one thing we can study and learn from, but we can never completely control it. And as we dream bigger, building taller skyscrapers, longer tunnels, and crazier locations, the job of the geotechnical engineer is only going to get more important. So the real question is, what are we going to try to build on it next?